pray. Father, thank you for this day and for our time to be here and to study. Please help me to be clear and concise in what I'm teaching and help us to learn. Pray for Silvio and Thompson with their schooling and whatever's next. Lord, would you just open the right doors and close the others, make it very clear for them. We pray also for everybody who's taking this class online, Father, that you just guide their steps. Help them with their future as well. We may ask this in Jesus' name. All right, well, where were we? We got off on the word entropy. Took off and never looked back. So we'll pick up there. Vapor, pressure, lowering. Remember what we wrote. I do know the word entropy. So, describe, what are we doing? I've been looking at this all day. You think I know what I want to say. The big thing with vapor, pressure, lowering is it is one of these colligative properties, right? So colligative properties. Right? Some of the most important ones, and the ones we'll be looking at today, are vapor pressure, which is, we're going to look at boiling point. We're looking at freezing depression. The key thing here is the interaction of solutes and solvents. So, we look at something like boiling point. You know, you've got these molecules in here, right? Let's say I have something that's positively charged, and it's interacting with my solvent, right? I'm going to do a solvent in green. So my solvent isn't nearly as free water. You should have figured that out by the shape. The solvent isn't nearly as free to just go up and to boil, right? And so that its vapor pressure matches that of the atmosphere, because it's bound, right, through intermolecular forces. And so we have to have enough energy to basically overcome these intermolecular forces so that it will boil. You gotta break all these, right? That's the idea of boiling anyways, right? Is especially when you think of water, you got to break all these hydrogen bonds. But the electrostatic forces at play here are even stronger than those in a hydrogen bond, right? And so you got to break all these for this thing to be able to boil. The same is also true with freezing, by the way. So if I had a solution of salt water, right, when it freezes and it forms ice, that ice is not salty. Right? You have to break all these attractions between the sodium and the chloride and the water, and you have to have only hydrogen bonds forming. And so essentially when I do that, you know, I've got to have like my Na and my Cl and my Na and my Cl, and I've got to just lock all these hydrogen bonds into place. You know, this is a terrible picture of this. But so again, I've got to do something about my intermolecular forces here. Well, I've got to get a lot, depending on the amount of solute that I have, I've got to drop my temperature a lot before these will fall out, and they will, you know, link up in a crystal structure, or these will cohere together in a crystalline structure. It's the opposite of this. Now, one thing that's interesting to note that you'll see coming up is the rate of boiling point elevation and freezing point depression aren't that well correlated. Often, the same amount of solute will raise this a little bit and will lower this like 2 or 3 times as much. Okay? So that's just an interesting thing to note. All right. Let's do this. Let's get after it. I'm so thankful that air finally shut off. By the way, you know we do not have much time left. Let's talk about that. So, today is Wednesday. You're not going to see me next week.
Through.
Monday we have off, and Wednesday I'm at state meetings at the BMA. So you will not see me again until like the following Monday, which is like the last.
Is it already like the last?
Yeah. So I'm just letting you know, and everybody know right now, we will finish, Lord willing, we will finish chapter 11, but that's it, and we're done. So be thinking about that right now, about doing the odd numbers on chapter 11. Obviously, if we don't get to something, I'm not testing you over it. So, yeah, here we go. Rolf's law, or however you're supposed to say this. We got almost all the vowels in here. E and I are missing. Rolf's law. The partial says that the partial pressure exerted by any component of an ideal solution is equal to the vapor pressure of the pure component multiplied by its mole fraction. All right, what are we trying to say? Partial pressure of each component, each part of an ideal solution is equal to the vapor pressure of the pure component, instead of pure part, times its mole fraction. Okay, so they give us this formula. PA equals XA times P star A, which does not feel all that helpful to me, where PA is equal to the partial pressure exerted by component A. So, component partial pressure of A is equal to mole fraction of A times the vapor pressure of pure A. Then it goes on to do some more fancy stuff with this. We're calling that the total pressure of a gaseous mixture is equal to the sum of partial pressures for all its components. That's Dalton's law of partial pressure. The total vapor pressure exerted by a solution containing I number of, could be X, could be whatever, of components is this. So the pressure of the whole solution equals the sum of mole fractions times the vapor pressure of the pure substances. Did I just write that wrong? No, that is right. Okay. All right. That is right. Okay. So what does this say? it's saying the vapor pressure of the whole solution is just equal to the mole fractions, which of course will come out to be 1 when I add them together, times the vapor pressures of each one. So this one times mole fraction, this one times mole fraction, this one times mole fraction. All needs to add up to, of course, the total thing here. That's not complicated. A non-volatile substance is one whose vapor pressure is negligible. So you think of something like table salt or table sugar. Negligible vapor pressure, right? And so the vapor pressure above a solution containing only non-volatile solutes is due only to the solvent. So if I have a solution of water and corn syrup's not volatile really, right? So appreciably at all. So if I have that mixture, then any vapor pressure in the in the atmosphere above it is due exclusively to the water, not to the cornstarch. But the cornstarch does matter because its interaction, the number of moles of it interacting with the water, is going to influence directly the vapor pressure of the water in a fixed way, according to our mole fractions and also according to a constant. So let's take a look at this. So it says compute the vapor pressure of an ideal solution containing 92.1 grams of glycerin, which is C3. You're going to want your periodic table in your calculator out, by the way. C3, H5, OH3, and I did write that right, 92.1, that's correct, okay. And 184.4 grams, I'm sure this is water. I sure hope this is water, but it might not be. Of ethanol, okay, which is C2H5OH. This is at 40 degrees centigrade. Vapor pressure of pure ethanol is, so the vapor pressure of ethanol at 40 degrees C is 0.178 atmospheres. Glycerin is essentially non-volatile in this temperature. Okay, so what are we trying to do here? We're going to use this stuff to calculate the new vapor pressure, right? So this glycerin, or glycerol, matters because it's going to affect my mole ratio, but it does not contribute to my pressure at all. So I'm looking for this, right? This is going to be due exclusively to this. So P equals the mole fraction of ethanol over the solution, right? Times the vapor pressure of ethanol, which is 0.178 atmospheres. Okay. So, actually, you're probably already doing that. But what is the molar mass of ethanol?
That's what I'm gonna do.
Okay. It actually made it very, very convenient for us. I'm going to write this up here for you, save you a little time. 92.094 grams per mole. Only. Can I write that down? Okay, this is correct. This is for glycerol. Excuse me. That's correct. And then down here, it is 46.069 grams per mole for ethanol. So this one we know is just 1 mole, right?
Mm-hmm.
So when I think about this, I've got 1 mole of glycerol plus however many moles of this. So 184.4 divided by 46 equals
184.4.
So we put 4 here, right? So this is my glycerol, this is my ethanol. I need ethanol divided by glycerol plus ethanol, right? So 4 divided by 5 equals 0.8. 0.8 times 0.178 atmospheres is going to give me my new vapor pressure. Okay. Is that the correct answer? It is 0.142 atmospheres. Okay. Good. Let's do another one. Some more drop the marker. I don't know where to go. The solution contains 5.00 grams of urea, which has a formula of, I should put that because that's going to confuse things, isn't it? Which has a formula of CONH2, which is a non-volatile solute, and 0.100 kilograms of H2O. Okay. So we have, if the vapor pressure of pure water at this temperature is 23.7 torr, then we need to calculate the new vapor pressure, assuming ideal conditions. So we know that our new vapor pressure is going to equal our mole fraction, right? It's going to be H2O, moles of H2O over moles of H2O plus moles of urea times 23.7 torr. Okay? And don't miss here that this is in kilograms and that's in grams, because that's going to make a big difference. So calculate your moles first, and then you get your mole ratio, and the rest is just a multiplication. Let me see if I can shut this air off. I've essentially got 5 grams. Oh, no, excuse me, I need to do that. No. I have 100 grams over 18 grams per mole, right? Divided by 100 over 18 grams plus 5.00 grams over what is the molecular mass of that one? We've got 12 and 16 gives me 28, right? And this is 14, 15, 16 times 2 is 32, so that should give me 60. And then this whole thing times 23.7. Okay, so 100 over 18 is 5.55.
Green.
And this one,
Yeah, 5.5.
this one is 0.0833 to give me a total of 523.42. Oh.
Yeah, that's right. That's about the same.
All right. Distillation. You familiar with distillation?
A little bit. I might remember.
So you got a solution and you want to isolate an individual component. Maybe you got two different liquids. So classic distillation involves grain alcohol.
To do liquor.
Hmm?
To do like liquor and stuff.
Yeah. So you're gonna do, you're gonna have a container here with what they call mash. And you know, it's gonna have some kind of grain, it's gonna have corn or rye or wheat or whatever, and a whole lot of water, and then some bacteria or some yeast. And so what you're getting here is a fermentation reaction. You're gonna have a whole lot of water, and you're gonna have a whole lot of dead stuff and waste, and you're gonna have a whole lot of ethanol. And so you're gonna filter out the best you can the waste and the junk, and you're gonna have a mixture here of H2O and ethanol and some junk. Okay. Well, how do I separate my water and my ethanol? It's not like I can filter it.
You vaporize it.
I gotta vaporize it, and I gotta rely on the fact that they have different vapor pressures, they have different boiling points. And so then I can have some means of capping this off. Maybe I've got a stopper in here with a tube that it's gonna go through, and then I'm gonna collect this, and classic still, this would be spiraled, but the one they show in your book, of course they're not showing a still, but we know that it's up. Now I'm gonna be able to collect it. Of course I want a thermometer in here also, because the boiling point of ethanol is going to be much lower than the boiling point of water. I know the boiling point of water is going to be when all the ethanol is gone, which it will be, but or should be by the time I start getting water actually boiling. Not that there won't be any water in the mix initially, because some of it's going to be there just based off of vapor pressure. But if I hit 100 degrees, I know I've got water, right? But if I'm boiling at 90 something, it should be almost exclusively ethanol, and I'm counting on that as this rises, the water vapor is going to condense and fall back down. So as long as I'm sub 100, somewhere in this range, I know that this fraction should be ethanol. And before this, as I start to see this rise, I need to get this out of the way. I'm going to collect a middle section, which is going to be a mush, and then the rest of it should be water. Now this is directly related to vapor pressures and partial pressures, right? Because ethanol has a lower boiling point, it's actually going to exert more pressure in that closed system. Now, there's probably more information than they wanted to give you, but it's more useful if you want to run your home still. So, let's do a little bit of this. Actually, they give you this and they don't do anything with it. They want you to know about distillation. They start talking about gasoline, which is cool. Different parts vaporize at different temperatures and rise to different levels in the system and all that. But I'm never going to do that at home. I could totally make grain alcohol if I wanted, though, which I don't. Do you guys have a word for that back home?
For the process?
For the stuff you make yourself?
Not really.
Here they call it moonshine or white lightning.
No. We have an alcoholic beverage that is basically that.
Yeah.
And it's called, like, if I translate the word, it's called pinga. Pinga is literally drop.
Okay.
How they made it, they have like sugar cane,
Okay.
and they do like, they distillate it, and then it just like drop into a bottle, and then they do it. It's like a Brazilian alcoholic beverage, and it's really strong.
I'm sure you don't know very much about it. All right, let's go.
It's strong.
Boiling point elevation. Okay. So the change in temperature, delta always means change, right? So the change in the temperature of the boiling point, so how much it's going to change, is equal to a constant, a boiling point constant, times molality. Okay, so essentially what we're looking at here is how much is a solute going to affect the boiling point, right? Well, it depends on how many molals I have of it. And I multiply that by a constant. Now this boiling point constant has nothing to do with my solvent. It has everything to do with my solution. This has everything to do with my solution. This one has to do with my solvent. And remember, it's independent of the identity of the solvent.